Now it's my pleasure to introduce Harold Schenk, who will be the moderator for today, and he will take us off to our first speaker. So Harold, whenever you're ready, the floor is yours.
Yeah, thank you very much, Hans, and a very warm welcome to all of you to this SPIE webinar on spatial light modulators and their potential for holography. Yeah, once again, my name is Harold Schenk, and I'm with the Brandenburg Technical University in Cottbus, Germany, and with the Fraunhofer Institute for Photonic Microsystems in Dresden, Germany. Today, we have 4 distinguished speakers from 4 renowned companies and organizations, respectively, and they will give us their individual view on the potential of phase panel spatial light modulator technology for holography. In recent years, there have been huge improvements in image sensors, computing power, and sophisticated optical design. There are numerous applications which are based on holography, ranging from metrology, microscopy, up to consumer applications. And the spatial light modulators are a key component for computer-generated holography in particular, because they are able to generate holograms dynamically with high bandwidth. So what are the requirements to be met by spatial light modulators? What is the status of this technology and what can be expected in the future? Is phase panel technology ready for commercialization? A question, by the way, we would like to know your opinion. We prepared a poll question on that at the end of the webinar. Okay, so I will start, and I'm very honored and pleased to welcome our first speaker, our keynote speaker, Bernard Kress from Microsoft. Bernard is the partner optical architect on the Microsoft HoloLens project since 2015, and previously the principal optical architect on the Google Glass project at Google 10 since 2010. He has also contributed to the field of optics for AR systems as an author and published several books on micro-optics and AR systems. He's chairing the annual SPIE AR, VR, MR event in San Francisco and the SPIE Digital Optics Conference in Munich. He has also been elected to the presidential chain of the SPIE in 2020 and is currently serving as its vice president. Bernard, thank you for making it possible to be here. We are looking forward to hearing your keynote on system architecture, requirements for computer-generated holography in wearable displays. Please go ahead.
Thank you. Thank you very much, Hans. Thank you very much, Harold. This is a great honor to be here and talking about this amazing technology, which is a burgeoning technology. And this is, so let me share my screen. And this is really in the title of my talk here. So can you see my screen? Yep.
Yes.
Okay, good. So let's go. So the title, I adapted a little bit the title for today's talk, and it's an introductory talk. I'm not going to talk about phase panels. We have many very nice talks following this one that will focus on phase panels. I will focus more on the architecture, the hardware architecture and the ecosystem that is around in order to bring these phase panels in a form factor and an architecture that can be wearable, for example. As for the AR display market. So, well, let's start to define things. What is MR? What is AR? What is VR? So we're going to talk a little bit more about MR, mixed reality. Well, mixed reality is really the blending of the physical and digital world in which users may interact with digital and real world objects while maintaining presence in the physical world. Today, this is very simple. You have your light field, which is your natural vision, and you superimpose on it a stereo display with a fixed focus, which is, by the way, 150-year-old technology. And this is the key technology behind nearly all the headsets today available. You can name Facebook Oculus, you can name Microsoft HoloLens, Magic Leap. They're fixed focus stereo displays, about 150 years old, but still blows out the mind of anybody, putting that display on. Today, we're talking about something that is a little further away than fixed focus stereo display, which is light field or holographic displays, which is really how you perceive the world, you know, and in a mixed reality where you mix your real world, which is a light field, and a stereo fixed focus display, of course, there's going to be vision comfort issues, and we'll tackle this. But first, we'll see why we're interested in mixed reality. Well, today, mixed reality is really transforming enterprises. Enterprises first, and then consumer. Consumer, we still don't know exactly how this is going to be packaged and delivered to the consumer. But for enterprise, we know perfectly. For defense, also, we know perfectly how to do this. So for enterprise, you know, remote collaboration is one key aspect of mixed reality: guided training and task management, training and simulation, sales assistance, design prototyping, and many others. You know, and really the return on investment for enterprise is cost avoidance with these technologies. So conventional display, and so we're talking about face panels, and you know, the title of this webinar is really a spatial light modulator. So let's look at some of the spatial light modulators that are available today to form these display engines. The display engine is really the engine that generates a display, and then there's a combiner that combines that display with your reality. Well, you have micro OLEDs, which is not really a spatial light modulator because it's an emissive display, but nevertheless used in many different devices, such as the Nreal smart glass today, the high temperature polysilicon backlight LCD, which was used in Google Glass V2. Front light LCOS. This is really interesting. It's a waveguide that illuminates the LCOS, and then the image goes through the same front light. It's basically a transparent illuminator. A backlight would be an opaque illuminator, which would be placed on the other side of the light modulator. Backlight LCOS, where the backlight is positioned at 90 degrees with a PBS cube illuminating the LCOS and then coming out. That was used in Google Glass V1. And then, of course, micro LED. Everybody's talking about micro LED, and everybody is excited about micro LED. You know, that can bring brightnesses to new levels, but they're not really ready, and especially in RGB mode. And you know, micro LEDs that can be grown on silicon. You know, there's a lot of challenges, but it's really exciting. Backlight DLP, you know, DLP is a non-polarization spatial light modulator, reflection mode. With a backlight can produce a lot of brightness. Free space LCOS. Free space LCOS is the technology that is used in most of the mixed reality systems today, including HoloLens V1, Magic Leap, and many others. LBS, laser beam scanning, is a technology that is starting to be used more and more. We use it in a HoloLens V2. North Focals also use it in their smart glasses. Intel Vaunt use it also. Companies like Microvision are using it. And free space DLP is really the one that beats all the records in brightness. Before the micro LED panels will really bring the full power of that technology in the next, I would say, 3 years or so. So display engine. Now we go to combiner. The combiner is very important because this is the optical element that combines the digital display with the see-through. Many companies are using waveguide combiners, such as us, Dispelix, WaveOptic, Digilens, and even Lumos. They can be diffractive, they can be made with volume holograms, such as Digilens. They can be made with reflective parts, such as in Lumos, in reflective waveguides. And this is a very hot topic today, as hot as the micro LED topic, which generated a lot of VC funding. And today, for example, WaveOptic, you know, is a company that got bought for $500 million, and WaveOptic designs great waveguide architectures. So you can see they were bought by a Snap. So you can see that you know, it's these two aspects. the display engine and the combiner are very, very hot technologies today. And we don't really know which one is going to gain traction. And today we're talking about yet another one, which is face panels. So let me start with vision comfort challenges. Well, let me talk about, there are many vision comfort challenges today, but I want to talk about vergence accommodation conflict mitigation. The vergence accommodation conflict is the conflict between the vergence of your eyes and the focus of your eyes. As I told before, most of the mixed reality systems today have a fixed focus. However, the stereo display can actually present the information. The stereo disparity can actually present the information at any distance. Now, if the distance equals the focus, let's say 2 meters in HoloLens or 1.5 meter in others, then the conflict is 0. If the stereo disparity presents an image that is different from the physical focus of the image, then you have a conflict that can be measured in diopters. Now, depending on which optometrist you're talking to, a quarter diopter is okay and will not produce any vision discomfort. So, for example, with a fixed focus at 2 meter, you can present information from 1.3 to 4 meters. Now you can talk to another optometrist that say half a diopter is okay, in which case for a fixed focus at 2 meters, you can present information from 1 meter to nearly infinity, 5 meter. But really what you're interested in is, at arm's length. This is 80, my arms are 80 centimeter long, I measured them. And this is really where it's getting interesting, because that's where you interact with the image. We call it hologram. It's not a hologram. We abuse the language as much as we can at Microsoft, but also at any other company. So when we talk about a hologram, it's basically a fixed focus stereo image. It's not a hologram. Face panel will really produce a hologram. So that hologram, that stereo image is located at, for example, 50 centimeter. And that's really where we need to reduce the vergence accommodation conflict to lower than half a diopter or so. We cannot do this with fixed focus stereo displays. Okay. So we can do it with a binary focus switch, which was done in Magic Leap 2, and there's 2 different focuses, and there's a vergence tracker. You can do this with continuous varifocal display. This was done in the half-dome prototype by Facebook Reality Labs. You can do it with a temporal light field where you switch very fast the focus between 4 different planes, and that was done in the Avegant prototype. It's a light field, but it's basically a temporal light field. If you stop time, there is no light field anymore. Retinal display scan is interesting. You scan the image with a laser, and then you have infinite depth of focus. That means that the image is in focus everywhere. Is this good? Is this bad? Well, there are 2 schools. And then, of course, there's holographic display near to eye display, which produces a real optical blur. And this is what we're talking about today. I advise you to see this video on YouTube. It's one of the first attempts at Microsoft at computer-generated holography. It's a SIGGRAPH paper, but it's a nice video that you can review here. 2017 by my colleagues Andrew Maimon, who's now at Facebook, Andreas Georgiou, and Joel Collin at Microsoft Research. And they developed an amazing display back at that time, 2017. This is a 70-degree field of view. It was done with a color sequence face panel. I believe it was from HoloEye, Aleto, I think. 70-degree field of view, real RGB image from face panel operating at a color field rate of 260 hertz. So you can see, this is a picture, so you can see exactly what you can do with a good CGH design algorithm. And there's not much speckle, not much Fresnel rings appearing, although you can see some there. This is an example of a amplitude and phase function as we encoded it on a phase-only panel with the double phase technique. So that was a LC, that was a LCOS, a phase LCOS panel. And you can see a zoom on part of that pattern. And then real-time RGB hologram calculation at 150 hertz. And of course, what this is a per pixel depth display, so you can set the focus of the camera that is looking. We use a camera looking at this image. The iBox was very, very small. It's a camera looking at this image, and then you can change the focus of the camera and see the different parts of the dragon. How it was generated. Focus at far distance, focus at close distance. We also did optical see-through version with a holographic optical element combiner, which was a photopolymer, panchromatic photopolymer, RGB. That's basically a reflective off-axis lens, as you can see here. 150 degrees diagonal field of view. Actually, it's not diagonal. I think, as I recall, it was horizontal, was achieved. Of course, there was a lot of aberrations, and the aberration can be corrected in the render pipe, just like here. The lens function and the aberration map can actually be included. So the lens function, what is the lens function? It can control, it can compensate vision correction. For example, astigmatism in the hologram. Of course, this is not for your see-through. You need something else there, but this is for the hologram. So vision impairment problem correction can be implemented, such as simple diopter focus or also astigmatism. And then on top of it, you have the aberration map to correct the aberration, and you include this in the hologram generation shader, and then you extract it to the face panel. We also worked on a compact AR prototype. So that's our cross collaboration between HoloLens and Microsoft Research, and we actually were able to build a very compact system here, where again we use a panchromatic photopolymer combiner, transparent, of course, and then phase LCOS with 2 mirrors, as you can see on the right. Meanwhile, a lot of work has been done in optimizing the real-time calculation of the hologram, such as here by the Stanford team. You can see that this is a step further than what we did at Microsoft Research. Venture capital firms are helping to grow this burgeoning, this burgeoning light field holographic AR headset ecosystem. So Serial, one of these companies, raised $7 million last year to bring a light field display to AR glasses. Another company, VividQ, partners with ARM for the real-time calculation of the hologram, received funding, and of course, I think in July this year received about 15 million or $20 million, I don't remember. It's 11 million pounds. And what is really interesting, they're also working on Unity plugins. Unity is the development platform for AR systems. So this is the other side. It's not a hardware ecosystem. It's really the software ecosystem that has to be generated at the same time in order to make this a reality for AR systems. Well, this concept is not new. There has been companies a long time ago, like 2-3 Photonics, which received grants to develop real-time full-color head-up display systems. Was bought by Dakari to integrate that HUD architecture into an AR system. Now, of course, that company disappeared from the radar. Other aspects of head-up displays using face panels can be seen here. A lot of money injected to this in these companies. Okay. So everything looks like hunky-dory, but it's actually not. There are still many critical challenges to solve today for the integration of face panel-based light field holographic displays in AR headsets. The first one, and we're going to talk about this, I think, in the next 3 talks, availability of low-cost face panels. It could be LC or MEMS-based or even different, Second one, availability of fast, non-iterative CGH calculation algorithms. So no IFTA in there. And this is linked to the third one for remote render compute that could be with a companion smartphone, or could be a thin client and then directly linked by 5G to the cloud. New data compression architectures need to be developed to pull this data from the cloud or from the phone directly to the headset. Speckle reduction hardware also and algorithms. There's two different schools. You can do it in hardware, you can do it in algorithms. You also have to, and we talked about this, we also have to choose the optimal combiner. And we talked about the waveguide combiners, which are very hot topics today. Now, waveguide combiner with exit pupil expansion, like all the ones that I showed you today, cannot be used with per pixel depth display, such as the one that we developed. That's why we did not use a waveguide combiner, because it will not work with pupil expansion. That's why we decided to use a single reflection lens, which is a flat holographic optical element combiner. So yeah, it would be nice to use exit pupil expansion in order to generate the eye box, but you can't. So comfortable eye box generation at large field of view is very difficult. And today I have no idea how to do this. So that's one other aspect of these challenges that are remaining to really bring light field and holographic display to AR systems. And AR systems today, I insist, do not produce any holograms, no matter what we say, what you hear on YouTube or wherever. These are fixed focus stereo display, exactly like in a stereograph from the late 1800s. So nothing changed. It's just that the photography is now digital rather than analogic. Thank you, and I'm looking forward to the other talks this morning, and I hope this talk gave you a good insight of what is still missing today as far as the optical architecture is concerned, to bring face panels as the solution for a light field / holographic display in AR systems, which could be a substantial revolution in AR and MR systems, and also smart glasses. Thank you.
Yeah, thank you very much, Bernard, for sharing your view with us on holographic displays, in particular on holographic displays based on spatial light modulators. So great overview, and I really liked your motivation with respect to the emergence accommodation conflict in the near field, because I think this really shows where the challenges are on the one hand side and where the potential actually is of holography. So actually you mentioned 6 challenges on your last slide, and I would like to ask which of the challenges do you see solvable within the near future, and where do you think real new ideas, new breakthroughs are required?
Well, there's 2 types of challenges, the hardware challenge, and then the display pipeline challenge, how to really talked about compression, data compression architectures for holographic data, which is very different from a regular MPEG compression. So that's one part. I'd rather talk about the hardware challenges, because I'm a hardware engineer. I'm an optical engineer, and I think one of the challenges that might be solved first is the generation of a suitable eye box in order to accommodate a large IPD, interpupillary distance population, so that a large field of view holographic display can be seen without precisely aligning the pupil. So an eye box of about 10 millimeters for a field of view of 50 degrees, or let's say 70 degrees would be great. Today this is impossible, but I have seen some teams working on very exciting architectures that are not based on traditional waveguide combiners as the ones that I showed you, you know, which are used now everywhere in mixed reality systems, but that are a little different. You can't use pupil expansion if your image is not at infinity. Now, of course, you can use a face panel and just project a Fourier hologram. You know, then it works. Then you can replicate your pupil. But then, you know, the benefit of using a face panel fades because it's a fixed focus at the infinity. So really what you want to combine is a per pixel depth image. And there you need to find a different combiner architecture, a little bit more complex than just a regular holographic reflective hologram, which will not enlarge your pupil, that's for sure. So really this one, I think, will be solved first. And this is one of the key aspects today in you know, in bringing this technology to a form factor that would be comfortable as a headset. That's the iBox.
Okay, great. Thank you for the comprehensive answer. I have one question in the question and answer section. So for everybody, please use the question and answer section. I see a further question or two further questions in the chat, but it's easier for me if you put it to the question and answer section. So the question here is about hologram resolution.
Good question.
The question is about how to maintain and control hologram resolution.
Yeah, that's a good question. I didn't touch this because I didn't have time, but I would have loved to touch this. And it's thank you for asking this. I think foveated resolution is one key aspect of any holographic display, and gaze contingent foveated display. Now, what does this mean? You increase the resolution where you need it in your foveal area, you know, and you scan your gaze, and you increase the resolution where you actually need it. And this is possible today with a face panel display. It's much more difficult with traditional stereo display, where you go from a Cartesian you know, plane to another plane, which is angular spectrum. But optical foveation is very difficult with traditional amplitude display systems. But really, you know, I love that question. And optical foveation, gaze contingent optical foveation, I think, is one of the challenges to solve. And this is a challenge that I have seen solved already, you know, in some prototypes. So really increasing the resolution where you need it and decreasing it where you don't need it.
Okay. Yeah, thank you very much, Bernard, for the answer in that detail. I have further questions in the question and answer section, so we run out of time a little bit. But if you're available during the other talks, maybe in parallel you would maybe answer the questions. I think that would be great. Thank you very much for that. So sorry to the others who ask questions, but you will obviously receive an answer from Bernard. Excellent. So we can proceed, actually. Thank you very much once again for this great talk.
Thank you,
Howard. And we will proceed with our next presentation. And our next presentation will be given by Stephen Harman from Silicon Light Machines in Sunnyvale, California. So welcome, Stephen. And you can maybe already turn on your video during I introduce you. So Silicon Light Machines, as you probably know, is located in Sunnyvale, California, which is the heart of Silicon Valley. And Silicon Light Machines is actually designing and manufacturing the products in this area. Stephen received his Bachelor of Science in Electrical Engineering from UC San Diego, followed by a Master of Science and PhD from Stanford University in the SolGuard lab. He's now an optical systems engineer at Silicon Light Machines, where he is investigating applications for new MEMS amplitude and phase modulator products. Previously, his research at Stanford University included beamforming techniques and applications in microscopy and 3D displays, as well as work in holography and novel lens fabrication. His talk is entitled High-Speed MEMS Spatial Light Modulators for Holography, So, Stephen, please, the stage is yours.
Thank you very much. Let me get the slideshow going. Oh, stop video. Start here. Okay. Yes, thank you very much. I'm Stephen Hammond, and yes, my talk today will be about silicon light machines, high-speed MEMS spatial light modulators with an eye towards holography. Silicon Light Machines is an optical MEMS supplier. We are owned by a Japanese company called Screen Holdings. And today I'll be giving an overview of our technology, including existing amplitude and phase modulators, as well as some stuff we have coming down the pipe. And then I'll go over some amplitude and phase applications to give you an idea of kind of where these modulators fit into the world. So broadly, the SLM technology, that's Silicon Light Machines technology, is comprises of the GLV grating light valve and the PLV planar light valve. The GLV is a 1D ribbon-based design. We have amplitude and phase modulators and some new phase modulators coming out. The PLV is a 2D aperture, so that's a 2D piston-based faceplates, and right now we have a linear controlled, that's a 1D controlled with 2D phase and amplitude coming out soon as well. So I'll go into a little more detail. The grating light valve, I say amplitude for that is because the active element is a deflecting ribbon. So the ribbon goes down, creating a phase modulation. By having these ribbons alternate with static or bias ribbons, we're able to create a phase differential, which creates a diffraction grating, which steers more or less light into the first order. By blocking either the 0th or the first order, we're able to get analog grayscale. These ribbons are capable of very high speeds, and they're only moving nanometers at a time. As I mentioned, this is really a phase modulator in an imaging or an amplitude modality. To create an arbitrary phase modulator, you simply remove the static or bias elements, and you do have to pull the ribbons down by a half wavelength instead of a quarter wavelength to get a full 2π shift. Right now, what we have in phase modulator is the UV vis device. So we've demonstrated up to 488 nanometers 2π modulation. The pixel sizes are a little large at 25 microns. What we have in development coming out, prototype coming out this year, is a up to 1550 nanometer 2π phase modulation capable device with much smaller elements and a large aperture. So we've already demonstrated MEMS feasibility in this bottom right. We've measured over 800 microns of deflection, meaning we have more than enough for 2π phase modulation up to 1550 nanometers. The planar light valve is the 2D analog of the GLV. Rather than having these 1D ribbons, we have 2D faceplates that are pulled down with piston action. This retains the high speed and analog grayscale for amplitude or phase if you just change the faceplate. We have demonstrated amplitude modulation and have an 8K device prototype coming out next summer. What we have available now is a linear controlled PLV. The linear PLV is a 2D aperture. So we have these 2D phase elements, but it is operated in a linear fashion. So it's a 1D amplitude modulator, which is very ideal for high power. You can focus it down for very high power scanning systems. What I've shown for the PLV so far, those were both amplitude modulators. The difference between amplitude modulation and phase modulation, again, is just a bias element. In this case, the non-moving space around the center circle creates a diffraction grating, whereas for a phase pixel, you would just have a square. This is our product line. I'm not going to go into too much detail. You can find it on our website. But when I'm talking about high speeds, I want to point out we're talking 100 to 350 kilohertz, depending on the electronics module. And yeah, you can find our products on our website. So first I'll begin with going over our amplitude modulator applications. Originally, the GLV was actually made for displays, far field projector type displays, laser projectors. The very high contrast enabled by the analog grayscale in first order, plus the high speed allowed very bright, large format displays, such as in planetariums by Evans and Sutherland, or that 10 by 50 meter Sony Laser Dream Theater. And it was achieved by using the GLV to pattern a line and then scan it with a mirror. We'll come back to that at the end of the talk. Right now, the amplitude modulator is used, the GLV and the LPLV both, in a wide range of other products. Usually it's going to be an application that can take advantage of the high speed for high throughput, often needing this analog grayscale or high contrast and high power handling. So we see the amplitude GLV in computer to plate, direct write, holographic printing, and the LPLV is in additive manufacturing, laser marking, and material processing. I want to focus on the holographic printing because we've got some nice slides from one of our customers, CI Tech. The CI Tech creates printed holograms. So these are essentially printed diffraction gratings using the GLV. So the high speed allows them to have a faster print time. And of course, they need the analog grayscale and the contrast to be able to make these prints. They use the GLV to print in photoresist and then create these really cool looking holographic foils, I imagine. For phase technology, we have demonstrations that are more in the academic world mainly, but we also have some demonstrations here at Silicon Light Machines. Right now, a lot of these demonstrations rely on beamforming principles. This is kind of what I like to call a dumb hologram. It's the hologram of a single, in this case, line. So to do steering in the far field, your phase modulator simply has a linear ramp, which you see here in this bottom left, that'll steer in the far field or in the foyer. For lensing, you have a cylindrical profile. It acts like a cylindrical lens. And then of course, if you just add these two profiles together, you're able to lens and steer in the far field or in the foyer plane. I will point out that though we have mainly been using the phase GLV in this method, it is a spatial light modulator. It can create any arbitrary phase profile. So at Silicon Light Machines, we've demonstrated time of flight send. That is, we've used it in the far field to steer. It's steering faster than you can see. It's a random access device. You can access any pattern at any speed. And so here we're just skipping every 20 lines. You could just do it completely randomly. These are lines being steered across the screen. So it's just simply when it's going so fast, it looks like a pattern. And then finally, this is a demonstration of steering and focusing at the same time. You can see the lines coming in and out of focus. My colleague at Stanford, Joseph Landry, made a really cool microscope using the high speed to sweep a light sheet in time with a rolling shutter. And by doing this, he was able to create 3D images in pretty much real time at submicron resolution. Additionally, a research team at CU Boulder used the phase GLV for focusing through scattering media. So through speckle media, they were able to create a focus. You also see they used it through a multi-mode fiber. The high speeds of the GLV are necessary to create the modal matrix to be able to focus like this. And you can imagine there's a lot of implications for imaging through scattering media or fiber, as they show here, or anything like that. Finally, we get to the 3D display application. This was actually my thesis at Stanford University. The idea is to take that old laser projector and replace the mirror with a phased GLB. And just as we showed with the beamforming, use the beamforming to sweep a patterned line at multiple depths instead of at a single depth like with the mirror. So creating a real 3D image, or a multifocal 3D image if you prefer. When I say real 3D image, I mean it creates a real image. You can reflect it off a screen, which is what we see here. It's a 405 laser, but it looks blue because this is paper, it's fluorescing. So the screen is close to the projection optics, the tree is in focus. You move the screen back, the S is in focus. To then create a direct view display, you add a eyepiece. So you have to take these real images and make them suitable for your eye, or in this case, a camera with a macro lens. By, not quite ready to strap to your head is kind of the point of this picture. By focusing the macro lens up close, we see the tree. Farther away, we see the S, or if you prefer, this is looking through a beam splitter. We see real life, that's the printed picture, of course, and then the virtual image. The dragon is in focus at 300 millimeters. The bunny is in focus at 1.5 meters. Another aspect of a 3D image is parallax. We show that by stopping down the aperture and focusing to infinity. That means the tree and the S are going to be in focus at the same time. But by moving the camera a little bit, the tree appears to move more. This is a very narrow field of view system, so it's actually going to be very dramatic if you just move the camera a little bit. As we can see here, the tree's about to fly away. There we go. And this parallax is really only in one dimension. It's a one-dimensional beamforming. By taking a CG image and clustering it into different lines of different focuses, we're able to create an animation. I'll point out that this beamforming approach was kind of the simplest approach for me to do. There is, of course, if you had more complex algorithms, holographic algorithms, you could probably make much more even interesting looking images. So in conclusion, high-speed phase modulators enable some unique applications. Of course, there's 3D display, which I'm very excited to get my hands on a 3D AR, but there's also applications in imaging and material processing, and we're hoping that the influence of 3D displays will benefit these other applications and vice versa. Also, Silicon Light Machines has been making phase modulators for 20 years. They just happen to have been in an amplitude modality due to the application space. Due to these new advances in computing, 1D and 2D phase modulators are now on the way very soon. Thank you.
So thank you very much, Stephen, for introducing us to the different applications and actually the technological and technical approach based on GLV and PLV. So I have two questions in the question and answer section for you. The first question is with respect to the, I would translate it to the bandwidth, probably of the PLV. So can you comment on that?
The bandwidth is determined by the electronics. So right now it's 350 kilohertz for the GLV. For the LPLV, I think that's more physically demanding. So that's more around 100 kilohertz. If that's, I hope I answered the question.
Okay, thank you. Yeah. Right, so then next question says that GLV was initially developed for projection. Now the question is for the PLV device, you mentioned applications like printing and marking. Is there also an attempt to use that for projection again?
So right now the linear PLV, that's the 1D control, is really we're really excited about the material processing and laser marking 3D printing space. The 2D control, I don't know if we have any plans specifically for projection. It's the initial one's going to be an 8K channel device, right? So it's 8,000 channels. So I think there's some very interesting applications in holography for an 8K channel device. For projection in general, you would need to probably add some other component. You need to scan it. That's probably not enough pixels to make a high definition display.
I see. Okay. Next question, maybe a quick answer here with respect to the fill factor of the 1D and 2D array.
The 1D fill factor is around, off the top of my head, it's around 80%. That really depends on the module. It's basically just, so for the GLV, sorry, let me correct myself. For the GLV, there's two flavors. One is a ribbon with a biased substrate. That, for amplitude modulation, can have an effective 100% fill factor. For phase, you have, of course, these ribbons, and there's going to be some gap between them. That'll generally be limited by our process, and right now that's around 80%, depending on the width of the ribbon. But we're working on getting that higher, of course. Because the face plates, the linear PLV, is well over 90%. I believe over 95%. It's a 25 micron face plate with a very small gap between with a very small gap.
Great, excellent. And I'll take the last question here. Maybe also a quick answer. The question is if you need a surface to project the 3D image.
If you need a surface to project the 3D image.
Exactly. So I assume that somebody's thinking of kind of retinal displays or so. So maybe you can elaborate a bit on that.
So so for my those last few images, those were direct view. It is, the real image is being formed somewhere in air. You do not need a screen. You can look. I did look directly at it. You do, of course, need a beam splitter or something like that. Otherwise, you're looking directly at the phase modulator.
I see. Okay, so Stephen, thank you very much for the great presentation once again. And maybe you can have a look in the chat, maybe some further questions arise, and maybe you can even give a direct feedback on the questions I already mentioned. So thanks a lot for sharing this insight. And we will now switch over to our next presentation. And I am pleased to introduce Stefan Osten from HoloEye Photonics in Berlin, Germany. HoloEye is providing products and services in the field of diffractive optics, spatial light modulators, and LCOS microdisplay components. Stefan studied microsystems engineering at Polytechnic in Bremen, Germany, and he received his diploma in 2003. And after that, moved to Berlin to work for HoloEye as technical sales engineer. He does sales for the SLM product family, including pre- and after-sales support, and he is also involved in SLM-related R&D activities. And Stefan, I'm sure everybody is especially interested today in your R&D activities. So the title of his talk is LCOS-based phase SLMs for holographic applications. Please, Stephen, go ahead.
Thank you for the introduction. Let me share my screen. Okay, the title of my talk is LCOS-based phase SLMs for holographic application. And I will start with a short introduction. Then I will briefly show the basics of LC-based liquid crystal spatial light modulators. Then I will talk about digital optics and the interface between the digital and the analog world. In the next part, I will discuss an important parameter to use a micro display as a photonic device. And in the end, I will show some related applications. To say a few words to the company, HoloEye is subdivided into 3 business units. So our roots are in the design and production of diffractive optical elements. The spatial light modulators are the dynamic versions, and they are based on transmissive and reflective micro displays for phase and amplitude modulation. And since all of the phase modulators, the phase-only modulators, are based on LCOS, liquid crystal on silicon displays, we work with the LCOS microdisplay technology in general. To remind you what a diffractive optical element is, it's a microstructure or a computer-generated hologram, etched infused silica or molded in polymers for mass production. And if you illuminate this microstructure with the monochrome light source, then a pattern will form in the far field. And you can generate a huge variety of different patterns with this approach. But of course, it's still static, and the next logical steps are the dynamic devices. Here on this slide, you see a few examples of different modulator technologies. It's a DLP from Texas Instruments for projection applications, and you see wavefront, so it's a deformable mirror for wavefront applications, a grating light valve that was just shown by the previous speaker, Mr. Harman. Then you have the piston type MEMS devices that will be part of the next talk, and HoloEye is concentrating on liquid crystal based modulators. Architectures are available. That's are the transmissive devices and reflective liquid crystal on silicon technology. And HoloEye focus on the reflective LCOS devices, since they have a significant advantages compared to the transmissive architectures, such as better light efficiency, faster response time, smaller pixels, and they can handle more power for high power applications and material processing. So here on the lower left part of this slide, you see the structure of a liquid crystal on silicon display. It's basically a liquid crystal layer sandwiched between 2 alignment layers. They are on top of a silicon backplane with the pixel electrodes, and all is covered with a cover glass where the transparent electrode is also contained. On the right part, lower right part, you see the basic principle for phase modulation using liquid crystals. Liquid crystals, they show electrical and optical anisotropy. And if you apply an electric field, the liquid crystal molecules tilt in the direction of the electric field. And if you couple linear polarization along the liquid crystal director axis, you can modulate the refractive index or the optical path lengths within the LCOS cell. What is then, in other words, phase modulation? If you now have a couple of, if you now have a pixel array, you can generate optical functions in a digital manner. That's why we call it digital optics, because you can create those functions digitally on a PC and transfer it to the SLM via a standard graphics card using video interfaces like HDMI or DVI. On this slide, you see 2 differential interference contrast images of 2 optical functions. On the left side, you see a part of a computer-generated hologram. And on the right side, you see part of a Fresnel lens structure. Well, this approach allows to address almost every possible phase function. And here you can see some examples for beam splitters on the left side and beam shapers on the right side. A gray level here represents a phase level, and the phase functions are addressed onto the SLM in modulo 2 pi. Now we come to the relevant SLM parameters that make a microdisplay to a real photonic device. This table summarizes the general properties of state-of-the-art liquid crystal on silicon displays, and the first 3 have the main influence on the quality of the generated optical function. With the resolution, you can influence the complexity, with the pixel pitch, the diffraction angle, and with the fill factor, the light efficiency. Here on this slide, you see scanning electron microscope images of a reflective pixel matrix. And on the right part, you see a close-up of a junction between 4 pixels. And you see there are interpixel gaps that absorb light, and it's also already a microstructure that diffracts light into higher orders that is lost. And of course, everyone wants to have those losses minimized. And here on this slide, you see a simulation for 2 different pixel matrices. On the left side, you see an 8-micron pixel pitch with 500 nanometer interpixel gap. On the right side, a 6.4 micron pixel pitch with 200 nanometer interpixel gap. And as you see, the diffraction losses are pretty much reduced for the smaller pixels with the smaller interpixel gap, even though I have to admit that those simulations are made for the infrared. But this already increases reflectivity from 65% to 80%. And if you can also consider to add a dielectric mirror coating on top of the pixel matrix, and this already increases, we have shown in the lab that this can increase the reflectivity up to 97% for a reflective phase-only display. So everyone is now asking for smaller pixels. But smaller pixels, they are not for free. They also have a certain drawback, and these are increased crosstalk effects for higher spatial frequencies. And on top of this slide, you see a simulation for 2 different binary gratings. So on the left is a coarse grating, and on the right is a fine grating, and you see that the effective phase stroke between the adjacent pixels is reduced due to the crosstalk effects, what limits the diffraction efficiency. On the lower part, you see measurement results for 2 different pixel sizes, 8 micron on the left side and less than 4 micron on the right side, and the very small pixels, they already show a significant crosstalk effects for very high spatial frequencies for the 1-1 binary grating. So another important parameter for an efficient SLM is the wavefront quality. And due to the manufacturing process, such an LCOS display is not perfectly flagged, so it shows some aberration. And at HoloEye, we use a high-resolution triming green interferometer to measure this wavefront deformation. And out of this measurement, we can derive a compensation function that, if addressed onto the SLM, can compensate its own aberrations. And on the lower part, you see the measurement results. The left shows a non-compensated display with a peak-to-valley value of around 1 micron. And for compensated display, you end up in 100 nanometer over the entire display. And on the right side, you see a measurement with a different temperature, with a temperature increase of 5 Kelvin. And you see that it's already or still quite good for this temperature change. So on this slide, I show you some measurement that compares a non-compensated and compensated display. Here we addressed a 5x5 beam splitter, and you can see that for the compensated display on the right side, the homogeneity in the generated pattern is significantly improved. So up to now, we have only concentrated on the active part, but it's also worth to consider the driving electronics. This LCOS-based technology has its roots in a projection industry where video interfaces are used. But to overcome the legacy of video architecture, we developed FPGA-based driver boards that offer way more flexibility for industrial applications, such as standalone operation or even calculation of hologram functions on board. Main such message of this slide is that such such SLM devices can also run in color field sequential mode. So with only one display, you can generate a color hologram reconstruction. And this enables a very compact design of for holography, for color hologram reconstruction for near-to-eye displays. So to come to the applications, here is the nice application again from Microsoft, where they demonstrated a prototype for a near-to-eye display. This was already discussed by Bernhard Gress, and I do not want to go too much into detail here again. And on this slide, you see another nice publication for holographic near-to-eye display that's from Stanford, and they use they work on hologram optimization, and they use two SLM devices in a Michelson arrangement, and that way that both SLMs are addressed in that manner that the zeroth order, so the undiffracted part, is eliminated by destructive interference. And this enhances the contrast of the reconstructed hologram quite significantly. Such phase SLMs are also can also be used as a diffractive beam shaping element, for instance, to convert a Gaussian input beam to a top-hat beam with a homogeneous intensity distribution, what is of benefit for material processing, like laser drilling. Here's a commercial laser marking head within phase-only SLM as integral part. So you can address computer-generated hologram to form a certain pattern in the far field. And the nice thing of this product is that it's very flexible, because you can feed in different pulse laser sources depending on the material requirements, if it is gold or glass or polymers. So as the last application, we go to the telecommunication. So this shows a wavelength selective switch. And this was for us the first real commercial implementation of a LCOS-based phase-only SLM. Here the SLM acts as a diffraction grating and does in fact beam deflection. And because of the high flexibility of such a reflective LCOS-based phase-only modulator, most of the current available wavelength selective switch products are based on phase-only SLMs. This was it, and thank you for your attention.
Thank you very much, Stefan, for that very interesting and comprehensive talk. And actually, thank you very much for sharing the very impressive application examples. So it's very nice to see that a lot of your phase modulators already are used in a wide range of applications, from telecommunication up to near-to-eye displays. But it was really great to see. So I don't have questions so far in the question and answer section, so please make use of putting your questions there. So I will start with one question, and that is, you already commented on a certain trade-off between smaller pixels and the needs from applications. So can you shortly comment on technical limits versus application needs? What is possible? What would be required? Are there some principal limits?
Yeah, of course, you want to have phase-only displays with very small pixels to generate a larger field of view with larger diffraction angles. I think state-of-the-art, the smallest pixel sizes that are available are 3 micron. But as I have shown, this may end up in larger crosstalk effects, and this will then limit the really effective resolution. So in terms of resolution, the maximum resolution what we have is 4160 by 2464 pixels, and of course would be beneficial for good holographic reconstruction to have 8K or even 16K devices, but development of such a pixel backplane is quite challenging, and one could consider to tile more 4 or 16 of those 4K displays, but then you have the challenges that there are the gaps between the single ACOS cells, and yeah, this would need to be overcome now.
Right. Okay. Thank you. Then I have a question here regarding the maximum average laser power that can be used with your SLMs.
This depends on the wavelengths. In the infrared, a customer used more than 400 watt per square centimeters, and in the visible we have shown 50 watt per square centimeter with versions with dielectric mirror coating. So a lot of customers working with pulsed light sources, and they for material processing femtosecond laser, and there's a limitation of a few millijoule for 1 picosecond or 500 femtosecond lasers, the 1 kilohertz regime.
Okay. The next question addresses the cost of the fabrication. So in the first presentation, cost of the SLM or the phase mode SLM were seen as a kind of barrier. Can you comment on that? So are there steps which are currently followed to reduce cost?
Yeah, since this is quite a mature technology, because it was developed for projection applications, it can be in volumes, it can be relatively cheap. But of course, development of a phase SLM, this costs some R&D activities, and that's why developer kits are not that cheap. But in higher volumes, you can go down to a couple of $100. But it's not a $1 or low dollar technology.
Okay. Yeah. Thank you.
The driver boards, that depends on the prices of the driving ASICs or the FPGAs. That are developed by Xilinx.
Yeah. Okay. Thank you. One last question I can take here. Once again, with respect to smaller pixels, the question here is how to reduce fringe field effects with small pixel pitch.
Fringe field effects, yeah. You can think about developing liquid crystals with higher birefringence to make the liquid crystal cell thinner, and this reduces crosstalk effect and fringing fields. But this is on the development of liquid crystal materials from.
I see.
We are working with companies together, but it's a chemistry task.
I see. Okay. Stefan, thank you very much for the great presentation and for answering all the questions. There are some further questions in the meantime in the question and answer chat. I would like to ask you to work through that, and it would be great if you could give an answer to all of the questions, if possible, if you're still available. Thank you very much again, and we will proceed with our fourth speaker for today. And our fourth speaker today is my colleague, Michael Wagner, from the Fraunhofer Institute for Photonic Microsystems in Dresden, Germany. Fraunhofer IPMS, by the way, is an R&D service provider, and among other things, develops application-specific high-speed, high-resolution micromirror arrays for different applications and wavelength areas. Michael joined Fraunhofer IPMS as a manager of product development of micromirror-based spatial light modulators in 2003. Since 2005, he has been heading the SLM business unit at Fraunhofer IPMS. Prior to this career at Fraunhofer, Michael worked on image sensors as project manager and technology development expert. He received his diploma and PhD degrees in electrical engineering from the University of Siegen, Germany. Michael, we are looking forward to your talk on micromirror arrays targeting computer-generated holography. Please go ahead.
Thank you very much, Harald. I hope you can understand me.
Very well.
Great. So I'll try to share the presentation.
Works.
Can see the slide?
Yeah, it works.
Okay, great. So welcome also from my side, the fourth talk here. and I will concentrate on micromirror arrays. So we've already heard about LCOS and grating light wave, and this is a complementary technologies in the area of spatial light modulators. So switch to the next slide. The outline of my talk. I will very briefly say something on the motivation. So we've already heard a lot of that, and so I'm not really able to add much to that. Then I will give you an insight in what Fraunhofer IPMS developed so far in terms of micromirror arrays, just a little insight. And then I would switch to the perspective to develop micromirror arrays, MMAs for holographic displays. I'll show you some first results of conceptual studies and give you an insight in what we are developing at the moment. And finally, I will conclude my talk. So motivation, not much to add here. If you just screen the internet for virtual reality, augmented or mixed reality, there are a lot of applications, and we already heard about that. It's really fascinating, and there is a high motivation there. The new normal, especially after the Corona situation, which changed a lot. Yeah, that's a strong motivation to contribute here, and especially to contribute in the area of spatial light modulators. For this application, what is nice, we already heard that, is 2D. More interesting for a lot of applications is 3D. So displaying of people, objects, etc. There again, stereo is good, but limited. We already heard that, low depth of range, probability of fatigue, and so on. Better in this respect is computer-generated holography, which enables more or less natural vision experience. Key component, also mentioned in previous talks, is a spatial light modulator, and amongst that, micromirror arrays enable high-speed polarization independence, and I will show that there are options for low pixel crosstalk, and that point was already mentioned concerning the LCDs. So we are closely cooperating. We're the experts for the spatial light modulator, for the microsystem. We are closely cooperating with holography experts, and what they tell us is they need a high number of pixels, very small pixels, more or less the smaller the better. Phase modulation is better than intensity modulation, and also analog is better than binary modulation, because you simply can't use pulse width modulation. So this all points at analog piston mirror SLMs. They might be perfect for holography, but we also saw that in the listing of Bernard in the beginning, no off-the-shelf devices were listed there, and in fact, no off-the-shelf devices are available, and that means development is needed. And so what is a piston mirror SLM? You see a schematic here in the lower part. And it's basically small mirrors, small platforms that are moving up and down. So what did we at Fraunhofer IPMS develop and concentrate so far? Developed various spatial light modulators, micromirror arrays for different applications. And you see some examples here on the upper left, 1 million micromirrors, tilting mirrors, frame rate 2 kilohertz, so it means 2000 times per second You can reprogram the whole chip. Here on the upper right, you see a line device, also tilting mirrors, and some smaller devices in the lower part of this slide. So basically, you have different options, different functionalities. Tilting mirrors with 2 tilt axes, not only one, and also piston type mirrors. That's what we are looking for in holography. And just as an example, here you see a sequence of surface profile measurements of a micro mirror array piston type in operation. So each individual mirror can be addressed individually, and the whole thing works in this case here at about 1 kilohertz, and this is of course sort of a slow motion. This is a test device, customer evaluation kit. It's a section of a small matrix. We call that a small matrix, 256 by 256, and with a 16 micron mirror pitch. And if you look at this and remember what I said before, high number of pixels, very small pixels, it simply means this is not holography ready. This is not holography compatible. That's why we need to do something there. Just to give you the overview, an idea what is necessary for such development, you need to do CMOS simulation, design, and manufacturing. You need to do the same for the MEMS part, MEMS simulation, design, manufacturing, and of course, combine that in what we call the monolithic integration on one chip. Then you have to look into chip packaging, various topics in characterization, on wafer, on chip level, electric, optical, mechanical, application related, and we already heard that also from the colleagues, external driving electronics is essential as well. And basically at Fraunhofer IPMS, we have control over more or less all these different activities. But as you will see later, we are also strongly cooperating with external partners where this is really beneficial. So a very important point is our state-of-the-art clean room. We are processing there high voltage CMOS as well as MEMS on top of that. And also essential for these small mirrors that we need for a holography dedicated device. We recently were able to install deep UV lithography, and this is essential because the pixels itself become smaller and smaller, and of course there you have much more freedom of design if your if your dimensions in the lithography are also shrinking. So this is essential, and it's not really typical for MEMS processing. So we started with some first feasibility study together with the company Serial. We are closely cooperating with, and I can only pick out one of the results where we looked into the MEMS architecture and the pixel design. We looked into parallel plate actuators. This is the first thing you come to if you start to design such a device. So here are different variants. You have parallel plates and put a voltage between these two plates, and then you generate a force which deflects the mirror. In the end, the simulations showed that these architectures show a comparable problem as already has been pointed out with the liquid crystals. It's crosstalk between adjacent pixels. So if you can simulate that and see if you have different potentials here between neighboring pixels, you also in MEMS structures get or have to take care of pixel crosstalk. So it turned out in the end of this study that a comp drive actuator is more suitable. Comp drive is not really a new thing, especially for larger, for scanning mirrors, for example. Comp drive is really well known. It's not so well known for matrix devices, for very small mirrors, but that's what we will go for. You have different pros, especially also, or amongst them, is also this lower crosstalk. The design you see here is a schematic. This will not be the design that is in the end really processed. So then we are happy now that we can start a development project. The abbreviation here is Real Holo. This project now really targets for the development of phase modulating micromirror arrays for real holographic mixed reality displays. This project is funded by the European Union. We are really happy about that. And on the right side, you see the consortium that we were able to bring together. There are really experts for all the different topics that I mentioned. Yeah, with this, we think that we have very good perspective and a very good basis for this development. So what are we heading there for? Just to give you an idea about some parameters of this new device. This is all preliminary data, so maybe during the project we have to adapt here and there. Pixel size not as small as has been mentioned on the LCDs. 4x6 is what most probably will be realized. But anyway, for micro mirrors, it's quite small. The pixel count 4,000 by 2,400, so quite large. Vertical deflection here, 350 nanometer, which then refers to double or which enables to modulate until something like 700, so 2 times this mechanical deflection, and the frequency quite fast in the range of 2 kilohertz of frame rates. That's what we are heading for, and we think that based on what we have developed so far, we have a very good chance to meet that. So, of course, we also have at least one target application scenario in this project, and here it's a holographic automotive head-up display. The idea is that the driver of a car gets additional information, for example, potential collisions, additional traffic signs, direction guidance, vehicle data, and so on. And the speciality is that the driver gets this information exactly in the right position. So that means information for an object quite far away is displayed far away, and information concerning an object closer to the car is with a focus closer to the car. So there is no need for adaptation of the driver's eye switching between the windshield and the outside world. So what we also look for, of course, is further future application scenarios, but this is the scenario we are concentrating on in this project. So time is basically over for my short talk. As a summary, we think that we are relative or well that we have a good position to switch from a lot of different applications now to micromirror arrays for holography. We think that micromirror arrays can play an important role in future computer-generated holography displays, and we are looking forward to contribute to that. So thanks to a lot of people, companies, partners, and so on, especially also here today for the webinar organizers, and of course also once again for the funding that we receive in the current project, where I gave you a little bit of insight. Thank you very much for your attention, and I'm looking forward for questions and, of course, also potentially discussions after the webinar. Thank you very much.
Yeah, thank you very much, Michael, for the very clear presentation and for sharing all the interesting properties and aspects of micromirror arrays towards holography. And it seems that with a application in the field of automotive displays, holographic displays might become available within the next whatever years. So before I take some questions here, I would like to come back to my remark at the beginning. So you heard now a lot about recent activities in phase SLMs and its applications. And now I would be interested if you think that phase panel technology is ready for commercialization. So we have here prepared a poll. Question is, do you think phase panel technology is ready for incorporation into commercial applications? And we would appreciate if you just mark your answer here, and we will evaluate your answers and present the results in a couple of minutes. So please take part at this poll, and I'm eager to see what your opinion is. Okay, now back to your presentation, Michael. I have some questions here. So let me start with a question regarding your remark that binary modulation would be inferior. So here the statement is that there are a couple of phase SLMs which are pulse width modulated. So can you comment on that?
There are clearly SLMs that are pulse width modulation. The point is that you probably can't use these for real holographic displays. So you really need the modulation in real time. You can't generate a hologram in timely sequence. What you could do, and that was mentioned earlier, is that you have different focus in 2 or 3 different depths. That's an option, yes.
Okay, thank you. Next question regards the reliability of large arrays of micromirrors. Can you comment on that?
Well, I can only say that we have at the moment spatial light modulators that are operating in very specific high-tech niche markets, and they are operated 24 hours, 7 days a week, all over the year. So there are good perspectives for high reliability of these devices.
Okay, thank you very much, Michael. I'd like to get a feedback from Dirk when we can expect the result of our poll.
I'm ready to share those results.
Aha, so that was fast. Excellent. So then let me thank Michael once again for his great presentation. Thank you very much also for answering the questions, and maybe you can also work through the questions in the section, question and answer section. There might even arise further questions within the next couple of minutes. So let's have a look. So obviously people are a little bit distributed with their opinion. It's interesting that 15% say, well, they are already ready now. And then we have a drop, and the majority actually says, well, it will still take a time. So it will take 3 years or more until these phase panel technology is really ready for commercialization. Very interesting. So, but I think that is actually a reflection of that what we saw today from the presentations. Bernard outlined that there are a couple of issues to be solved. There were 6 challenges which have to be solved for near-to-eye displays. and also from the other presenters, we saw that there is a lot of development ongoing. But on the other hand, I have to say there were also a couple of examples where phase spatial light modulators are already used for commercial applications. Maybe not in that what everybody thinks holography is, but at least in the gray zone of holography, I would say. So if I just think about this telecommunication example we heard, and even this holographic printing, I mean, this is the area of holography. So yeah, thank you very much for taking part at the poll. And I would like to thank all of our speakers once again for these great presentations, for answering all the questions. I know it's always difficult to spend time. I hope that all of you who listened to the presentations received it well, and I hope that your expectations were met. And now I would like to pass over to Hans for the outro for today.
Thank you very much, Harald, and thank you, Bernard, Stephen, Michael, and Stefan, for the excellent presentations and for the very, very interesting discussion. This was a great webinar. We learned a lot. There's a very, very broad spectrum of things that we talked about. So I'm very grateful to all of you for your presentations, and thank you for all of you that that have attended and participated with your questions. As we mentioned at the outset, this is sponsored by the Journal of Optical Microsystems. So if you're inspired by some of the topics we talked about today and have some interesting research results in this area or in other areas in optical microsystems, we'd be very happy to see your manuscripts or maybe even have you participate in the journal as reviewers. So thank you, everybody, for attending. Thank you for the SPIE staff for bringing off the webinar without a hitch, as is usually the case. So I'm very happy how it went, and I wish everybody here in Europe a good evening, everybody in the States a good rest of the day, and I hope that we can welcome you to another webinar very soon. So a very good day to everyone.
Bye, everybody.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.